Hello, and welcome to the New Technologies in Mathematics seminar of the CMSA at Harvard University. So today we're delighted to have Jordan Ellenberg from the University of Wisconsin, and he'll tell us about his collaboration with DeepMind, where they produced, again, really new mathematical results in a collaboration between a computer scientist and Jordan mathematician. So as I always do, I'll watch the chat, so you can put questions on the chat. I assume you'll stop for questions.
Yeah, I'm happy to take questions. And it can be pretty informal. So I'm happy to take questions in the middle or at the end or some combination.
And put up a note if there's a sound problem. We'll try to deal with that. So there'll be some discussion at the end. So let's begin. Jordan.
Okay, hi everybody. Thank you for coming. Like both the people who are in the room with me and the people who are on the screen. And this is going to be, as I said, this is going to be kind of an informal talk about a collaboration I was part of with a bunch of folks at DeepMind. So I'm just going to, there's too many names on this paper to list, so I'm going to say sort of everything here is like joint with DeepMind, the corporate entity. And let me start. So I'm going to talk about a project that I did in collaboration with them, a project about the application of machine learning methods to a question in pure math, extreme combinatorics. So I'll start by sort of talking about what the problem is, but certainly in less depth than I would if I were giving a math talk. And in some sense, I mean, I'm curious, the people in the room, there's like some people I know who I know to be mathematicians. Are there like a bunch of people who would identify themselves as computer scientists here too? Okay, so some, like that, not a lot. I mean, in some sense, the goal of my talk is at least part to sort of try to, because for a lot of mathematicians, this kind of work is new and like working with folks in this area is new. I want to sort of give some kind of a feeling of what it is like for mathematicians to be involved in this work, partly because I thought it was like pretty cool and fun and enriching and interesting. And I would like to encourage more mathematicians to sort of get involved and participate in these kinds of collaborations. So I'll be giving, I think, kind of like a sunny view of how I see the potential in this work. But
or maybe enlarge when you're writing the word by factor of 2 or 3.
Oh yes, okay. I'll just make it small when I'm giving somebody else credit, and then I'll make it big when I'm putting. No, okay. So yeah, but let me start just by sort of talking about the particular problem in combinatorics that we sort of set out to work on, which is a problem I've thought about a lot in various contexts, which is the problem of top sets. And if it can be expressed very simply, the question is, and actually I'm going to sort of restrict to one very special case. So if anybody out there in the ether like is a sort of specialist in extreme combinatorics, yes, I'm only saying sort of one special case of this problem. But for me, a cap set is a subset S, and more generally, one might take any finite field. We're just going to focus on the case of Z mod 3Z to the n. Such that no 3 distinct x, y, z in S satisfy x plus y plus z equals 0. So there's a certain excluded equation. And if you've never thought about this kind of thing before, this might be like a little bit like, why this? Like, why would you study this particular question? In some sense, it's a model for lots of combinatorial and extreme questions involving triples of things. I mean, somehow here we sort of see this big fundamental fact of math that like there's a wall between 2 and 3. Right? If you just want no solutions to x minus y equals 0, they just have to be distinct. But 3-term equations are like massively harder, sort of for the same reason that tensors are a lot harder than matrices. And if I were giving a different kind of talk about work on this problem, I would actually talk a lot about the tensors and how notions of tensor rank are sort of fundamental to making progress in this question. Maybe I'll just make one cultural comment, which is to say that because 3 equals 0 for the rest of this talk, I could also write this as, let's see, negative y equals x plus z, otherwise known as 2y, sorry, equals x plus z. 2y equals x plus z, right? Because 2 is equal to -1, or y equals x plus z over 2, which is another way to say that x, y, and z are an arithmetic progression. So one reason that this is just historically is a popular question is because it's really asking that no three elements of the set be an arithmetic progression. And so this was seen for a long time as a model for the very traditional problem in additive number theory of what can large subsets of the integers look like, which have no three in arithmetic progression. Turned out in many ways not to be such a good model for that problem after all, but that's sort of like part of the historical interest. Okay. So the question is, how large can such an S be? That's what's called the cap set problem. And maybe it's actually worth, okay, we're gonna do something a little bit elementary, but in order to understand what kind of problem this is, which I sort of think is relevant for sort of thinking about what it looks like for machines to work on it, let's just do one case and so let's do the case n equals 2, dimension 2. I can draw z mod 3z squared. It looks like tic-tac-toe. Okay, so we have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. All right, maybe I should have said, I'm going to stop here for 1 second and say, the actual reason I got interested in this problem, even though I am a number theorist, was not because I was interested in sets of the integers with no three or an arithmetic progression. It's because, and some of you may know this, this is sort of also a model for the card game set, which is the 4-dimensional version of this thing. And so the a cap set is also in 4 dimensions is also known as a set of cards out of the 81 cards in this game in which there's no legal play. So there's certainly a popular folk question among players of this game about how many cards can there be, which sort of turns out to be sort of a rather subtle question, to which I initially had in mind the wrong answer, which I'm now going to explain. So, but let's think about this case. Well, first of all, what's excluded? Like, when do 3 things sum to 0? Well, here's 3 things that sum to 0, right? 0, 0, 0, 1, and 0, 2. And this is the only fact you need to know about z mod 3z for this talk is that 0 plus 1 plus 2 equals 0, because 1 plus 2 is 3. So I'll sort of draw this. This is excluded. But also by the same lights, like, right, 0, 0 plus 1, 1 plus 2, 2. Now in all 3 coordinates, you have 0, 1, 2. So this is excluded too. And so I could draw like a lot of things that are excluded, and it starts to look like tic-tac-toe, right? So let's literally, if you've never thought about this problem before, I really want this talk to make sense. So can we like literally take 1 minute, and I'm going to time it to try to sort of find the biggest subset that you can that doesn't have any solution to this equation, and then we'll sort of reconvene. And okay, I started the timer. Okay, so let's and then you'll have a feel for the problem, and then we can move on. For the people on Zoom, nobody in the room is looking at each other's paper, I can tell. So I hope you guys are also. Okay, we're done. What do we get? How big of a set do we make? How big of a set do we make? I see 4. I see somebody holding up 4 fingers over there. Okay, a lot of 4s. Okay. Okay. This is like you can see this is like a good applied audience. So 4 is the biggest you can get. Sometimes people say 5 or even 6. I sort of try to fool people by not drawing this one, which is also a solution to x plus y plus z equals 0. So it's a little bit more than just tic-tac-toe. But yeah, and there's lots of ways to sort of to mark 4 of these 9 guys such that there's no solution to x plus y plus z equals 0. Well, I say there's lots of ways, but actually z mod 3z squared has lots of symmetries. So there's really only one way, actually, like whichever ways you guys wrote down, they're all the same. But an easy way, and I have lots of colors, so this is nice. An easy way to make such a set is just to sort of do this. Because you see, if I only use 2 of the possible digits, if I only use 0 and 1, then it's actually very clear that you can't have any non-trivial solutions to x plus y plus z equals 0, because within each digit, I guess I did the snooze instead of the stop, sorry. Now I think it's done making that sound. Right, so any 3 of these guys, the last digits are going to be some combination of 0s and 1s, but if they sum to 0, that means they ought to be all 0s or all 1s. That's true in both coordinates, and so actually the 3 elements have to be distinct. So certainly, that's why I said distinct, because otherwise x plus x plus x is always equal to 0 mod 3, so you want to exclude that. So indeed, the set 0, comma 1 to the n in z mod 3 to z to the n is always a cap set. So the size of the largest one is always at least 2 to the n. And I think lots of people, certainly me, when you first encounter this problem, you're like, okay, well, that's pretty big. I should just prove that that's maximal. For example, if again, in combinatorics, what you would often do is say like, well, let's just kind of heuristically argue. You sort of like lay down random points and how many points would you expect to write down, and still have no solutions to this. And actually, from that point of view, it's surprising that there's one that's this big. If you argue heuristically, you would sort of conclude, oh, maybe about like root 3 to the n is as big as you could hope to do, but this is clearly bigger. This is like already 2 to the n. So this is already a sign that sort of some of the usual methods of extremal combinatorics are not going to work, because the large cap sets somehow are quite special, much better than you expect to see by chance. So let's make a little table where so here's n, and here's f of n equals size of largest cap set in n dimensions. And well, in dimension 1, it's kind of clear the best you can do is 2. In dimension 2, the best you can do is 4, as you just convinced yourself. But already in dimension 3, something interesting is going on. Let me sort of draw a little cartoon of it. Ready? So here's z mod 3z cubed. And of course, in each slice, you can have at most 4. But it turns out that if you sort of array these carefully, this is kind of a fun exercise, you can leave space for just one more in the extra slice. So you can actually get 9 in this way. And for 4, the answer is 20. So that's the answer to this question about the card game. The 20 cards is the most you can have without any legal play. And by the way, I'm pretty sure in the entire 30-year history of this game being played, I don't think a configuration of cards like this has ever occurred naturally. It's like extremely rare. Right? So one reason that people find it surprising is that in real life, when you play, once there's 15 or so cards, it's shocking if there's no play at that stage. 5, we know is 45, 6 is 112. I'm almost out of room, but I'm also out of values of n for which you know the exact answer to this question, actually. So, I mean, let me emphasize, right? So if you were to be like, then the computer scientists already are like ahead of me here, but if you were to just be like, why don't you just check? This is a finite problem. Yeah, it's finite in a sense that it's like literally less than infinity, but practically it's not finite, right? In any reasonable sense, the number of subsets of z mod 3 to d to the n is like 2 to the 3 to the n. That's infinity, come on. And maybe it's like Aleph 0, but it's definitely infinity for all reasonable purposes. So you can't do this exhaustively. I think you can kind of do this one exhaustively if you're careful about pruning and are willing to do a little bit of work. But these two are like actual theorems, that you have to sort of make some argument to do. Actually, interestingly enough, this is the hard one and this is the easy one, simply because this is actually so big that it's not, once you find it by some kind of like, there's some kind of crazy Steiner system or something that sort of you're able to massage into giving you this. It's surprising that there's one that's big, so it's not so hard to prove there's no other one, whereas this is just kind of like maybe about the expected size. And then, for 7, we know it's at least, at this point, these are theorems, but the theorem is an example, right? The theorem is like somebody made one, and this is how big it is, and that's what we know. Yeah.
Well, when you were saying 2 to the 3 to the n, right? But aren't there something you can just easily rule out to make this a much smaller complex problem?
Yeah, it's a much smaller infinity.
But it is still quite large.
But it's still, I mean, like, if you worked all your life to make 7 feasible, then I would say, like, what about 8? And then you would just be hosed. It's like that level of combinatorial explosion. But yes, I mean, you can do stuff, and that's the kind of involved, I think, in like these results. But getting an exact value is certainly expected. So what do we know? I emphasize that we certainly know that f of n bigger than or equal to 2 to the n. But actually something a little bit more than that is true, because it's easy to convince yourself that if I have a cap set in dimension m and a cap set in dimension n, I can take their Cartesian product and still get another cap set. So actually there's kind of a convexity here, which is that f of m plus n is at least as big as f of m times f of n. So this is just really this applied to adding 1 to itself a bunch of times. So in some sense, one way you can get lower bounds for this problem is you just go and find the very biggest example you've ever seen, like relative to this dimension, and then you take lots of copies of it. You can do a little bit better than that. There's sort of some kind of sophisticated ways of twisting these products a bit. But basically, I think I didn't actually write down the numbers, but there's like, there's lower bounds of the form, something like 2.218, I think, to the n, and like this is there's a version of this from like Adel in the 90s, and sort of, it's actually kind of hard, but every once in a while so even just in 2023, there was somebody slightly improved this number a little bit. In terms of upper bound, so from the point of view of pure mathematics, that's what I worked on, and so my sort of first real engagement with this problem. So for a long time, it was an open question. Well, okay, first let me say one theorem, that even this theorem is not trivial, that f of n is little o of 3 to the n. Isn't that amazing that even that is not obvious, that you can't have like a positive proportion of 3 to the n that satisfies this? So I mean, let's write that down. So f of n is, and you can get it as sort of on order of like a constant over n times 3 to the n. This is a result of Meshulam, also from the 90s. And for a long time, it was an open question whether you could do much better than this. This is actually a resultant in harmonic analysis over Z mod 3Z. It's a very clever trick about like the L4 norm of the Fourier transform of the characteristic function of your set. And so I think for a long time, this was sort of thought to be a problem in harmonic analysis. That's how it was thought of, and people who worked on it were mostly people in this area. But for a long time, it was open whether there was any exponent less than 3 for which you can get an upper bound. So a theorem of myself and Dion Kleisweit, coming off of a very big advance by Croat, Levin, Hodge, show that in fact you can get a better exponent, something around a little bit bigger than 2.7. So this is myself and Kleisweit. Sorry, this is getting a little small. but it's you know, it's me, so it's okay for it to be small. But one reason I think people think of this problem as an interesting one for computer investigation is that these are still pretty far apart. And not only are they far apart, I would say there is no consensus as to like which is likely to be closer to the truth. There's a lot of combinatorics problems where we kind of morally know the answer, but proving it is very hard. Here, people truly do not know what to expect to be true. Yeah, Mike.
This is a shot in the dark, but is there any relation between this problem and any version of the famous complexity of the matrix multiplication problem?
So great question. I think that I don't think there's a direct relation to the two, but there's a very interesting paper by Josh Grochow, who's in theoretical computer science, and a bunch of other co-authors, which I won't be able to come up with them off the name of my head. Jonah Blasiak, I think, is on it. Tom Church is on it. He used to work at Renaissance, actually, or who does work at Renaissance. Where there was an approach to fast matrix multiplication that people thought might be promising, and you can use these methods to show that that approach doesn't work or doesn't give better bounds. So that, and both have to do with like ranks of tensors. And by the way, for those of you who are like DeepMind alpha fans, I mean, the reason I got into this with DeepMind is that they have like a wonderful paper about tensor rank and the complexity of matrix multiplication using kind of alpha zero methods from last year, which has many of the same authors that are on this paper were also on that paper. And that was sort of how I got involved with them in the first place. But I don't think there's a direct relation between the two problems that I know. Okay, good. Where are we on time? We're at a good place. Okay. So having set this up, let me say something about what we did and the work that that I did with DeepMind. I told you that in this problem, a lower bound is given by example, and machine learning offers us many novel methods of search, which in particular, I think have shown in pure math that they're good at generating interesting examples. So we're going to work totally on the lower bound side today. And maybe I'll just comment that sort of now we can say 512 instead of 496. If you're going to ask, did I notice that 512 is a power of 2? I did notice that. I have no explanation for that. I don't really necessarily think that's the actual answer. It doesn't seem, the set doesn't seem to have anything to do with any, you know, 2 to the 9th, but that does happen to be the biggest one we were able to find. And now for the latter part of the talk, for the rest of the talk, I'm going to sort of talk about like how this was done, what was involved, and what I feel like I learned from it about the prospects for making progress in this type of problem using machine learning. And I should also say, I'm not going to talk about it today. We also slightly shaved this number upward a little bit, like somewhere in like the 2nd or 3rd decimal place, but like not by very much. Not because of this example, but as sort of in some other way. Okay, so I want to sort of focus right away on what I see as the central novelty of this work, because if you have some familiarity with like alpha type techniques like AlphaGo and AlphaZero, you might have an idea about how you might approach this problem. You might say, well, maybe like putting down these points and seeing how is like, you know, it's like some kind of game where you're like, my move is like, what's the next point I put down? And I sort of try to learn what's a good strategy in a traditional AlphaZero type way. And this is done a little bit, you know, some way of sort of searching, you know, the set of possible subsets that way when you can't search it exhaustively. So this is something different, which when they told me they wanted to do this, I thought was, I'm going to be honest, a pretty stupid idea, but it worked pretty well, which I find quite interesting. And so I'm going to tell it to you and you guys can tell me what you think. So instead of traditional methods of searching the space of subsets of F3 to the n, which is again some gigantic space, but we know that sort of these machine learning methods are often good at sort of finding interesting things in spaces that can't be searched exhaustively. We search, maybe also put search in quotation marks, and you can determine for yourself whether you consider the protocol I'm about to tell you a search. The space of programs looking for programs that output large cap sets. And I want to emphasize that by programs, I literally mean programs. Like I literally mean chunks of Python code that are not very long, like usually 25 to 50 lines or something. But you can imagine sort of some piece of Python code running it and having the output be some subset of z mod 3 to z to the n. And it's trying to find programs that do a good job. And how do you do that? Well, we now know that by contrast with the kind of alpha zero type methods, these large language models are very good. I mean, they're kind of good at producing chunks of English text, but what they're really good at is producing chunks of Python code, right? That's like absolutely their strongest feature. And so that's what we did. Let me sort of draw a little cartoon of the method. And then maybe you're going to have lots of questions about implementation, some of which I'm going to answer and some of which I'm going to punt. So, so this is kind of the basic framework is a genetic algorithm. Certainly a well-worn technique for generating interesting examples. And here's what you do. You sort of start with some set of some large number of random programs. I don't actually remember how many of them. So let's say like 1 million, like somewhere in that. I mean, I don't literally mean like random strings of text and then you try to get Python to run them and see what they do. I mean, you sort of have to do something to make it be a program whose output is a subset of CMOD 3 to the n. And then you look at them and sort of run them all and see which ones do best. So sieve down to 1% top performers on the capset task. And already, by the way, there's some ambiguity in what I might mean here. Yeah, here. Oh yeah, okay, good. So this is a problem I'm going to want to come back to that I could not get DeepMind that interested in. We're going to talk about it. So, so let's, at the beginning of the day, let's fix n. Like let's say 8, since that's one where we had good success. Oh, maybe I should say I erased it, but for n smaller than 8, it also does, it also finds the maximal ones and equals the best known one for 7. So I mean, so for the smaller numbers, it's sort of, I mean, we weren't able to get it to beat state of the art for larger numbers, but it also does sort of instantly find the big ones for the smaller end, yellow end. It seems to not matter very much, so I don't actually know what they look like. It's kind of like a base. It's kind of a base case, and then like, yeah. So I literally don't know like where they, like how they made them, but not from any not from. They're not any good. Like not because they're not, I promise you, that we're not building in secret domain knowledge about the problem. Okay.
Does the language model generate them?
It might just be that the language model generates them with like essentially no prompt except write a program that outputs a set, and I don't care what it is. Maybe I mean, but I truly do not know. So here I'll just emphasize that there's different things you can mean, and like they try different things. So in any kind of problem like this, you could say you're disqualified if there's even one solution to x plus y plus z equals 0. And then among those who are not disqualified, you look for the ones that produce the largest set. Or you could say, I'm going to impose some penalty for violations of the cap set rule and have some kind of trade-off between. I mean, there's a lot of different. One thing I learned is like in comparison to what we do in pure math, I mean, this is more like engineering, where there's like a lot of fiddliness where you have a lot of choices to make, and it's not, you don't necessarily have like a principled reason. You just like try different stuff to see what works. So I just want to sort of, again, I'm sort of speaking a little bit to the mathematicians here and being like, how does this feel different from what we usually do? but you have some notion of what it means to how you rate your things. And then you have, so this is like a smaller set of programs, 1/100th size. And then you have the LLM step. And what you say to the LLM is basically like more like these. And maybe if I'm to be a little bit more precise, what they found worked well, and this is sort of the sort of genetic algorithm part, is they take high performing programs, they take pairs of them and give it to the LLM and say, like, here's 2 chunks of Python code, like, give me more like this. Just like write another program that's like these. I want to emphasize, it's not saying these generate a large cap set, give me one that makes an even bigger cap set. It's just trying to sort of imitate. It's just saying like this. So one thing I find fascinating about this is that, oh, and maybe you, I mean, so, okay, so then now you have a big set again, right? Because the large language model, and then, you know, that's almost the whole thing, right? And then you sift down to the top. I guess maybe I should have made this arrow go to here, because you're sieving down to the top 1% again, you have a smaller set, and then you just keep on doing this. I really didn't think this was likely to work, and it worked pretty well, so I find this pretty interesting. Let me also comment, I was going to say, when I gave this talk in Wisconsin, like my colleagues who are, you know, mostly in like computer science and engineering, they asked like a very fair question, which is like, wait, so Ellenberg, like, what did you do? Like, none of this, like, this is honestly what DeepMind knows how to do. Okay, that is a very fair question. So I'm here looking at these programs that take place. So my role in this is, in some sense, is to look at the code that's being generated by the LLM and sort of try to talk to DeepMind about, like, what is this code trying to do? Like, what is its strategy, and like, what does it have to do with like what we know about these problems? So, I will say I like to give board talks. The one disadvantage is, and I will say, if you're at home, you can do this. If you, I hesitate to like suggest that people in the room like whip out their laptops or something, but you can do this at home or whatever. If you look at the paper, and look at figure 4, you can see. I mean, I think it's good to actually like see what this code looks like to make it not very mysterious. And I'll say another role that the mathematician has in this loop is to maybe look at what the code is doing and try to get ideas. If you're like, oh, I sort of see what it's trying to do, and maybe we could actually like build that in and lock it in as a strategy and sort of like get a little bit of better performance. And that actually, we had some luck on that for the kind of shaving of the lower bound upwards that I told you about before. But I gotta be honest, for this kind of task I've described here of just like finding individual large examples, one thing that is maybe a little bit humbling for the pure mathematicians in the room is that I had a lot of ideas about stuff we could build in with prompts and kind of instruct the large language model to make code that did. For example, this problem has a ton of symmetry. I mean, like Z mod 3Z to the n has an automorphism group of like GLNF3, which is a huge group. Everything about this problem is invariant under that. So I was like, well, obviously we should sort of tell the machine some invariant functions of sets of points, like sort of some natural things. None of that helped, at least in this problem. It was like a little bit humbling, but I mean, it might work well on other problems, but I'm going to tell you a little bit about how this code actually works. And I hope you guys are also going to be as surprised as I was that this worked well. Yeah, Edgar.
So, can you summarize what kind of program we're being asked to do?
Yes. So you guys are going to laugh, but so one thing is, now that I've sort of given the overall cartoon, I do want to say a little bit more about, not really details is too strong, but to sort of narrow it down a little bit. We always found that you needed to work with like some kind of skeleton. If you didn't put any constraint on the structure of the program, they found that it basically sort of spent all of its time sort of trying to figure out what kind of program to do and not really optimizing. So they use what's called a skeleton, which is like some part of the code is going to be fixed, and then there's like another part that's allowed to vary. Here's what every chunk of code we ended up using. Here's the form it had. Well, okay, before I say it, like what would you do if you, a human, were trying to make a large cap set? You would like put down some points, try to figure out, okay, where is there room for more points? Like try to figure out, maybe I should be careful when I think about putting, if I'm trying to figure out where to put the next point, let me look at the points I already have. Let me sort of figure out what would be the consequence of putting down a point here. I want to maybe be sort of redundant, so I'm not eliminating too many points, but whatever. But in particular, you certainly would, when deciding where to put down the next point, you would consider the current state of play. You would consider the points you already put down. Okay, these programs don't do that. That's like extremely strange. Let me sort of show you what the skeleton is. The skeleton that worked, and I promise you they tried a ton. So skeleton, the code always sort of, has something that sort of says, it defines some priority function, and the priority function is just some real valued function on the vectors. So then there's, some 25 lines of code or something that takes as input an element of z mod 3ac to the n and outputs some real number. Okay, so that gives you a way to put the vectors in order. And then what does it do? It just like lays them down in that order. It's like whatever one has the highest priority, I'll put that one down first, and then the next priority. And then the only way that this current state is used is it does check whether it's allowed to do it. It's like if the priority tells me to put this vector down, let me check it doesn't form a cap set violation with anything I've already put down. If it does, like skip to the next one and keep going.
You have to be a little more specific because it's a very big set that you're evaluating priority. Does it search through that set? Does it calculate priority?
So it's not a very big set because the priority is a function of the vector. So it's only 3 to the n. 3 to the n is pretty small. It's 2 to the 3 to the n is big.
Searches through the whole thing.
Yeah, so it's a function which takes as input an element of z mod 3z to the n, and then like literally it would just be like, okay, you start, the way this function would look is something like, okay, like we start at 1, and then if the first coordinate is equal to the 7th coordinate, multiply by 1.5, but if the 5th coordinate is this, subtract 20 or something like that. I mean, it all kind of looks like that. And
It doesn't have to search and make that list of high priority vectors. They just could do them all. And then it ranks them. And then suppose it comes down the list and it gets one which would fail. Does it put that one or does it skip it?
It skips it.
It skips it. Okay, that's the biggest set it can't add to the top priority.
And actually, it was kind of fun just while we were trying to see what this thing was doing. We actually did a lot of, I would sort of ask them, show me a chart of like, is it, as it goes through the vectors, is it just sort of like laying down the sort of first like 400 vectors of priority and then it doesn't add any more? And the answer is no. Like sort of sometimes there was sort of, it skipped a whole ton, but then there were some low priority ones there was still room for, and it would put them in. I mean, I don't know what to make. We did a lot of just like sort of psychological probing of these things to see how they were getting their performance. Yeah.
If you have this priority function in skeleton where it's defined is having a traditional priority function search that's not over programmed, but just over.
Yeah, so this is a great question, right? Because once you sort of, if you were to sort of on day one concede that this was the kind of strategy you were going to look for, you absolutely could sort of do a more traditional genetic algorithm search on functions. And I don't know if they sort of like went back and did that after the fact. So that is a good question, right? Because I make this whole thing about how it's not sort of searching traditional things, it's searching programs, but then in the end, what worked best, it's a little bit different for this other part of the problem with the sort of, with the exponent in the lower bound, but like, for this thing, yes, it ends up, not for lack of trying other things, like searching a pretty simple space. But I do want to say, actually, let me just, this is responsive to your question. So, I mean, a question we should ask at this point, which you kind of just implicitly did ask, is like, well, why actually do it this way? Like, especially once we see sort of which programs are actually successful. And I do think so. I went to a big conference last summer at the Simons Institute on interpretable machine learning, at which I learned that there's no definition of interpretable machine learning, and we don't know what it is. But like pornography, we know it when we see it, right? So this is definitely more interpretable, right? I mean, a sort of chunk of Python code is more interpretable to the human eye than is like some function which like literally just like to the 3 to the 8 vectors like assigns a real number to each one. If you looked at that, your eye would just see it as trash. Whereas if I look at the program, I can see, oh, for some reason it's rewarding vector, coordinate 1 being equal to coordinate 7, and it's rewarding coordinate 2 being equal to coordinate 6. So I do want to say, again, for the mathematicians, the psychological experience of looking at this code, and I'm not like, philosopher enough to make a claim about what's actually going on, but you do feel like the code is trying to do something. You do have some sense as a human mathematician that you're interacting with it and maybe trying to get it to express itself a little better. And, again, it sort of doesn't matter like what our psychological account is. I'm just saying in terms of, is it useful for us? Like that makes me feel like it is. Okay, I'm going to say more stuff, but I'm going to answer questions first. Yeah, Mike.
Well, another twist on the question. I mean, this is a conceptual mathematical strategy, which mathematicians could have tried before. I'll construct a function and do this. I might have to test it on the computer, but you might have some idea what function you might have constructed. Did anybody try that before in math?
I think as somebody who has worked on this problem, I would have thought it was too stupid of a strategy to try, to be honest. But again, I mean, somehow like, right, because I would say I want the pure mathematicians to like back me up so they don't think my intuition is crazy. This is a completely symmetric problem, which has a transitive group of automorphisms. So I'm like, obviously no vector is better than any other. They're like all the exact fucking same. Okay, sorry for losing people. I mean, so to me, it's like very weird to do it this way. So I learned.
So not even that was kind of.
Right, like I don't think this was sort of on the way. Yeah, Edgar.
Yeah, but it's back to genetic, because I'll ask my question before, like, when you go to back to these, you could just genetically optimize your priority, and then go back to the machine and like, write me code that give me more or less, can beat this priority, static priority. So then you can get again, a code that tries to do the same thing as you obtain from somewhere else. So kind of, does it make sense? Like, you can always reverse engineer whatever answer you get from the genetic optimization.
No, I didn't understand the question or the comment.
So abstract the priority function.
Mm-hmm.
Someone gives you a static priority function, some random numbers for each vector.
Yeah.
You can always go back to the LLM, write me a code that tries to match, give me some equals to each, and then you can get the logic again, right?
So are you saying like if I give you the function numerically, ask the LLM, give me code that produces it so I can sort of see what the.
Like in 5 lines or something like that.
Yeah, so we didn't try that, and it's a good question. That strikes me. So I don't know what happens. I mean, this is some question that's actually much deeper than Cap said about like Kolmogorov complexity or something, right? Like I give you some function on a large set and then say, can you write a short program that produces this function? I mean, wouldn't you be shocked if that were easy? I mean, I don't know.
No, I don't think it's easy, but I think it's like, in some way, trying to beat the function. If you give a priority as a static function, you're trying to beat that priority function. So now you can go to LLM, like, try to beat this function with some short code. So in some way, you can improve your, like, 1% CV.
Well, so, I mean, I'll say one thing. I mean, I find it surprising because to the extent I know anything about optimization, I sort of think of optimization as a process where like the machine learning part is trying to optimize. That's kind of what you're saying. You're saying, ask the LLM, do better than this. I'll just point out, and I find this strange, that in some sense, that's not present here, right? The optimization is taking place in some sense just here, where we're doing this purely mechanical process of just like seeing how big of a capset they make. There's no machine learning at all here. And the machine learning part somehow is just a likeness generator. And you're not, I mean, I also find it weird that you're somehow winning by not really asking the LLM to sort of try to solve the problem. That's done by this sieving step. So maybe there's definitely one more kind of psychological message. All right, what are the things I want to say before we're done with our time? Because this is just going to be sort of a bunch of slogans. So let me try to make a kind of hierarchy of stuff that what could have happened when we started this project before we knew what was actually going to happen. So in some sense, the kind of holy grail. This is is that a grail? It also looks kind of like a toilet, which I guess maybe depending on your view on machine learning is either a grail or a toilet. Would be I want to emphasize that right. This skeleton is a def priority B, but remember I sort of said fixed n. So maybe the first line is really like n equals 8. Okay, so one thing you should be asking is like, well, what if I take this out? And then having learned this function, I just run it on other n, right? This is sort of the big question. To what extent do you generalize to unseen cases? And I like to give something to the optimist and something to the pessimist. I feel like I've given a lot to the optimist. For the pessimist, I mean, this definitely does not work at present. It absolutely fails to generate from one n to higher n or lower n, for that matter. So the holy grail would have been, so protocol learns a program that gives good results for all or infinitely many n. And that, I really didn't think that was going to happen, and indeed it didn't happen. And by the way, so like another place, what value was I providing to this collaboration? Another thing that I can do is they can write a program and run it for n equals 8 and n equals 9 and n equals 10 and give the answer. I can look at the program and like actually prove like what does this do for a, like if you ran this for a general n. So and that's something I think that if you had a sort of fixed function for a fixed n, there wouldn't really be a sensible way to ask that question. Whereas if you have like a program that you could have run for any n, you can ask that question. And it gets stuck in an interesting place. I want to tell you. So no. So in fact, all their programs, when run for a general n, the ones that are any good, tend to yield some constant times 2 to the n. So they get stuck at this interesting place. And I want to emphasize that this is definitely way better than Randa. It's definitely learning something about the problem that it does this, but it's also not learning something. The two things I'd say from sort of reading a lot of this code and trying to sort of answer the question, what does it know about this problem is, again, as I said, it definitely doesn't know this is a vector space over a finite field. It doesn't know that there's a GLN. It sort of knows the symmetric group. Like it sort of knows that you can permute the coordinates. I think it sort of understands that. It sort of thinks of it as a vector space with a basis, if you like. So in particular, what it really, as you can maybe guess from this form, I think it really doesn't grasp that you can put together smaller solutions into a bigger solution. I think some of the LLMs will call that like compositionality, right? Or something. So I think that's what it's really, none of this code is able to get that. I think there's certain things it's doing where if I really squint and really put on my most hopeful face, I can sort of say there's some kind of like rudimentary prokaryotic version of that maybe it's kind of like struggling to grasp, but like mostly no, right? So this is it's sort of it's stuck at some place that I still feel like it's kind of cool a machine can do, but definitely like you know, and a human who had like thought about math before like could do it, but like maybe a person who hadn't thought about math before couldn't. So I mean, there's something going on here, but like not like this. So what's like the subgrail? And this I kind of hope would happen. Yeah, Aaron.
Did we try optimizing it for 5 through 8 and then seeing if that generally is better?
I as if I'd planted it. So this, I got to tell you guys, another interesting thing for those of us in pure math, working with industrial folks, is that there's some ways in which kind of the things we get excited about align, and there's some ways in which they don't. So this is the exact experiment I always wanted to do. And now that the GitHub's on the repo, like maybe we will do some of it. But like, right, I was always like, what happens if we sort of train simultaneously on like, 7, 8, and 9, n equals 7, 8, and 9, for instance? I mean, you can imagine two things happening. Well, you can imagine a lot of things happening, but you could imagine, oh, maybe then it generalizes a little bit better. Maybe it's learning something that does something for 10 and does something for 6. Or you could imagine it gets confused by that and just delivers trash and gives something that's like worse performance on all of them. I do actually want to know which one of those is true, and like we never did that experiment, because I think from DeepMind's point of view, it's more exciting to beat state of the art in a specific case, and so they really focused on that, training one n at a time, which is like totally valid. Like I have my interest there, so, but I love that. I mean, I want to do that. Okay, but now you maybe forget the other thing. Okay. Oh, right. So let me say a goal that I think is much more reasonable than this, that I would find very exciting, and which we kind of, I think, came close to getting to here, but didn't quite get to, which would be the following. Protocol learns a program that gives me an idea what to do for general N. This, I think, is much more promising. And I want to, I guess the sort of psychological report is that when I read these programs, there definitely were moments in the course of our work together that I looked at the program and I was like, oh, this is an interesting thing it's doing. I sort of feel like I see what strategy this is. Like, does that strategy do something for general N? Now, I will admit that if it had, then I would be telling you about that. But let me put it this way, it's generating stuff that's interesting enough that somebody like me who was like really thought about this problem pretty hard, felt like, oh, okay, this is like a novel idea that I want to sort of spend an afternoon thinking about and see if I can sort of get some juice out of it. That to me is like pretty exciting, actually, and makes me feel like pretty happy about the potential of this kind of work. It's also the kind of thing you can't put in your Nature paper, so I'm just like telling you here and now because I think mathematicians will care. But it made me feel like, I mean, and then of course somehow, in some sense, at the bottom of the hierarchy, but like good enough for Nature is, you know, be state of the art on specific N, which is which is already like pretty cool. But at least to me, so I'll sort of close here because we're going to the end of our time. This middle zone is what I'm most excited about. Like, I don't. Nothing we did here sort of makes me feel that I'm not going to say it's impossible, but it doesn't feel like within reach that these kind of methods are just going to sort of like spit out the answer for us like this. But this, which involves this kind of repeated computer-human interaction with both always in the loop, I feel pretty excited about, and I feel motivated to sort of continue doing these experiments. And I'm gonna, with sort of a group of researchers I have at Wisconsin, with sort of maybe some like lower profile but more accessible problems in extreme combinatorics. And so I think my big takeaway for the mathematicians is that this is maybe like a really interesting direction for mathematical practice that I feel like actually is kind of within reach with the kind of technology that we have access to like on our laptops now. So I'm going to close there and like take questions. Thank you guys so much.
Questions?
Yeah.
Maybe like an intermediate way to do this between Python programs and that and a function.
Repeat the question.
Oh, so we'll finish the question and then I'll repeat it for the Zoom people.
Which would be like to do some sort of like circuits that are non-uniform, like with gates. Do you think you would lose some of the interpretability you get in circle bullet point?
Okay, so the question is, it's not intermediate on this chart, it's intermediate between like literal chunks of Python code and just like lists of numbers, which is how you can describe a function. Yeah, so something intermediate between that would be like, an algebraic formula or a circuit diagram. On some level, I don't know if this is going to be like a non-answer. I almost feel like it depends how big the circuit diagram is, because if you sort of think about what a traditional neural net does, it is kind of like that. You're learning a function, but not like an arbitrary assignment of real numbers to real numbers. It's some like big ass circuit diagram called a neural network, right? That has like lots of weights and like with some finite number. And I think certainly it seems to be that those things at the size where they start to actually solve the task are not really human interpretable, right? I mean, people stare at, I feel like staring at the weights has not like given us that much insight. On the other, I mean, but as I said, these programs are pretty short, and in some sense, that's why the one good thing about giving a slide talk is if I showed you, you'd see that in some sense these programs, they are kind of circuit diagram-like. I mean, all they have in them is like if-thens, and if this coordinate plus this coordinate is that, multiply your score by 2.71 for some reason. So I mean, they're not like richly thought out somehow. They do. I mean, they're not that different. Yeah, there are sometimes for loops, but they're pretty simple. They're usually, if a for loop appears, it's usually like add up a bunch of things in a row or something like it doesn't always know how to like use like Python's sum operator. I mean, it's like, I mean, it does like, I mean, it's fun looking at these, you guys. I mean, it's kind of like, I mean, it is Python code and it runs, but it's not quite the way we would do it. But yeah, I think that circuit diagram model is I mean, on a different problem, we might see different kinds of code, but that's kind of similar to what we actually see. Yeah.
For say, for n equals 8, how does it change as you change the finite field? Do you understand that?
So we ran absolutely 0 experiments on any field other than F3. Just because that's the kind of most classical version of the problem where it's, I mean, in some sense, once you go beyond F3, there's actually like lots of problems. And so it's not clear sort of which one is the right analog. And I think they wanted to sort of focus, again, I mean, they wanted to focus on one thing and like beat state of the art on an existing problem that that's well known. But I think actually just talking to Yufei, actually, I mean, like once the paper's out, then you can talk to people. I mean, oh yeah, the other thing for the pure mathematicians is like, there's a goal of like, which I think now is sort of within reach of like, we don't want it to be the case that to do this, you have to like go through DeepMind every single time, right? That's like too much of a bottleneck for like actual mathematical practice. And you definitely don't want to like sign an NDA every time like I had to do. So I mean, they have put like the basic structure of this like in a GitHub. You can go like look at it yourself. And as I said, I'm working with my group at Wisconsin to sort of try to like just build out a test case. Okay, can just like a bunch of people sort of at home in a math department with their laptops, like sort of run some successful experiments of this kind on maybe easier problems, just to make it go. But wait, what was the question? I had an answer. Oh, Yufei, right. So I mean, but once it's out there, there's all kinds of questions for like larger fields that are very natural and where interesting examples would be interesting and whether it's sort of like less papers than there are about CapSet. So I mean, I really am hoping this will like provide value in that kind of sense. Yeah.
Yeah, there are 2
Right.
questions and a follow-up. Did you try just neural network for this function?
So I didn't, but if you want my guess is that they did before and it didn't work. So I don't quite know like what else they tried before I came in.
So now your approach, let's take n equals 8. How many programs roughly did it generate before you got this winning?
Oh, good question. So I don't know the answer to that question. Like how many cycles of this it
Yeah.
went through? I don't actually know.
Is it in the paper?
Maybe. They would show it to me. They would show me like the best ones they saw. I think they would like run it until it seemed to not be doing any better.
It's in the paper.
And yeah, and then that's when I would see it.
And the rest took like days, I guess. Anyways, I'll look at the paper, but
Yeah.
so the follow-up sort of depended, but I'll ask it anyways. So suppose you got many functions that produce, an optimal solution. Are they in some sense the same function, or are they in some sense different function?
So I'm trying to remember if there were, I think they only got the 512 once, but in some other similar cases, I think there was a case where there was a tie and we worked out whether they were the same. But there's actually sort of an interesting philosophical question, which is that there's 2 questions. Is it like the same set or the same set like related to each other by some symmetry? Versus is it the same program? Like I think it's like 2 different programs that happen to produce the same set. I'm not sure we should consider them
There's
the same.
different versions of the question.
Yes.
What was it considered?
And I would say, I don't remember there being, I mean, the ties were rare, but I don't remember there being a situation where we really were trying to assess are 2 programs kind of the same program. I mean, that's sort of, it's not really a well-defined notion, but yeah.
No questions? I opened it to the Zoom audience, but I didn't get any chat. So, if a Zoom person wants to ask, I think we would hear you. If not,
I see something in the chat, but it might just be people saying hi.
no, it's just me. I've been watching.
Oh, that's you, okay.
Yeah, yeah. Oh, okay, well, in that case, let's thank Jordan. Next week, we'll have Preetam Nakaran from Apple will speak on Zoom only about transformer models and their RASP interpretability conjecture. generalization conjecture. See you then.